Well, thank you very much. And we just found out what friends are all about, being able to make changes in the last minute. What I will do within this maximum 20 minutes is two things. I will summarize why the search for non-invasive prenatal diagnosis was so difficult, sometimes frustrating, and it's a fantastic time to speak about it because now it's finally there. So I can document that we really started more than 20 years ago. This was our first contribution. This was trying to figure out by dilutions using probes for the Y chromosome how frequent these cells are. And the answer is 1 in a million. So in every pregnancy, 1 of a million cells is from the child. Why are we so motivated to go after this for 20 years? Well, the explanation is clear. If we do procedures, let's say chorionic villus sampling, this has been compared to amniocentesis. It's equally safe in experienced hands than amniocentesis, but amniocentesis itself has a risk of 1%, and I think in this meta-analysis it was rightfully said that we tend to underestimate the true risk because there are no other randomized trials on this. So the whole concept of non-invasive diagnosis was an easy one. It was just to isolate the cells from the maternal blood, then maybe doing metaphase analysis or at least to do FISH, looking for the number of chromosomes. And I will tell you why this failed. The concept, of course, was clear. We go for material that comes from the villus tree through the intervillus space and through the maternal veins. It will be in the maternal circulation. The question was which cell type to go for. We could go for trophoblasts, but there are no good antibodies. They are multinucleated. So we looked for the nucleated erythrocytes because the fetus has many. There are antibodies available. We can stain for fetal hemoglobin. We can sort them out by using these micromagnetic beads. And this was 4 years later. And we could show, yes, you can enrich them all the way into the first trimester, but look here, sometimes there are dots here on the 0 line, sometimes these cells were not present in a sample of 15 cc. Another 4 years later, this is clearly a fetal cell from the maternal circulation, fetal hemoglobin, X and Y, but can we diagnose trisomies? Well, I think this was fantastic that the right trial was done at the right time. An NIH trial started exactly when these first reports appeared. Ambitious trial, 3,000 cases, 5 centers, and the result, not clinically too difficult, not clinically practical, and this did not get into practice. Why didn't it work? Now we know. It took a long time. It didn't work because the nuclei, even if they are still present in the erythrocytes, before they are expelled, they are already so disintegrated that the FISH doesn't work. So we learned a lot about the ontogeny of these cells, but it didn't work. We were sitting on the wrong horse. So then I think something happened that we can only learn from. Somebody remembered work from another field. These were plant geneticists in Geneva, Anker and Stroon. They had shown free DNA in the fluid of plants. And then Dennis Lowe was smart enough to realize that this might also be in pregnancy. The first application was rhesus. The problem here is easy. We want to know whether the child is positive. If the mother is negative, it's a big gene. We have to look for different exons, but you will be surprised that already in 2001 the specificity was 100%, sensitivity not, but that doesn't matter because if we don't have enough DNA or if we are too early, we will notice. And now there are about 7,000 cases in Europe of rhesus, non-invasive from maternal blood, and it's very rewarding to see that following this series, for example, 2005, there was no false positive or false negative, more than 500 cases. Now in these more than 7,000 cases, the accuracy is higher than 99%. It's even more accurate as if you type the blood directly. There are reasons for that because you examine on the gene level. So this is really rhesus, the first example where non-invasive diagnosis finally has entered clinical practice. It's there, and it's almost a pity if people don't think of it and still do invasive procedures for that. We have also applied it to KEL. KEL is more difficult. It's a single gene problem, but it can also be addressed this way. Now, if you can do this, then you could also go for the fetal gender. You can make a sex determination, and this is, of course, important in X-linked diseases, because if the mother is a carrier, 50% of her boys will be affected. Girls cannot be affected. And you know that by ultrasound you cannot do it before 14 weeks. It would be nice to know at 11 weeks. And the same here, already starting in 2001, the first series had a pretty high accuracy, above 96%. Now I would say it's also above 99%. And this has led, for example, in one single center in Paris, already reported in 2006, to a series of 1,800 cases where they used it in situations with X-linked diseases where the mother was a carrier. So number one on the list was Duchenne muscular dystrophy, of course, followed by hemophilia and so on. And you can just imagine one case here. This boy has hemophilia. He already had a problem with his knees from the hemophilia. When his mother was pregnant with her, we did the non-invasive determination, found her to be a girl, so she didn't have to worry after 11 weeks of pregnancy. And you can imagine that there is a high anxiety in these families. And sometimes I think we have to watch it, what we do in obstetrics. We pay an awful lot of attention to this segment of all the 2 to 4% birth defects, the chromosomal abnormalities, especially Down syndrome. We do nuchal translucency, we do biochemistry. It's all important, but in aggregate, it's less than a quarter of all these malformations that we see. This is the sum of all the single gene problems, and by far, of course, the biggest group is structural anomalies, like, for example, the diaphragmatic hernia that Jan de Prest will speak about, heart defects. And so maybe we have to get a little bit better also in the other sectors. And certainly in the heart group, there are many genes that we can look for. So if you add it up, I think what we can do already non-invasively is equally important than the aneuploidies. Now, what about autosomal dominant condition? Let's say the father carries the gene. Then, of course, it should be possible to show in the maternal blood whether the paternal gene is there. This was the first example that we did, Dr. Lee in our lab. He has achondroplasia. She has a 50% risk when she's pregnant with him. So this is the signal in her maternal blood showing that this child was also affected. There was no reason for her to terminate. She just wanted to know to be prepared for the delivery. Here you see the blot. This is in the affected man. This is in the maternal blood. So clearly the mutation was inherited, and there is myotonic dystrophy and so on. We see more and more cases. Now, what about autosomal recessive? This should be impossible because now mother is carrying the gene as a heterozygote. But let's say in beta thalassemia or in cystic fibrosis, there are so many genes that often the father carries a different mutation from the mother, and then there is also a 25% risk for a so-called compound heterozygote. And now, by excluding the paternal gene, you can find out whether the baby is affected or not. And we tried it for beta thalassemia because in Europe and other parts of the world, it's a very prevalent disease, 150,000 babies being born every year. So we tried to go for the compound heterozygotes. This started in 2005. Again, Dr. Lee, the first author here on this paper. And we could show that this works in the vast number of genes. And I think we will see these lists very soon where non-invasive diagnosis can be applied already. And these machines, you know, this mass spectrometer, company Sequenom got the patent from Dennis Lowe. It also got our patent of size separation. We found that, you know, the fragments of the DNA in the fetal compartment are in the lower segment, below 500 base pairs. So this is the distribution, whereas in the fetus, it's more to the left. And so these are all steps that make the diagnosis so accurate these days. And this has now been applied to cystic fibrosis, to Tay-Sachs, and so on. I want to finish by coming back to the chromosomes. Of course, the original aim was to diagnose chromosomal abnormalities, aneuploidies. Is this possible? Well, you could think of some fancy techniques to do it. You could go for mRNA and then do a dosage analysis because, you know, there are two alleles of one chromosome 21 and the other one. So there should be a disequilibrium. This was done by the group of Dennis Lowe, but to work with RNA is much more difficult than to work with DNA, so I'm personally a little bit skeptical whether this is the way to go, even though we have all tried to do it. Then an idea came up independently in two places. Dennis Lowe's group, but also Quake at Stanford, and this was to use digital PCR. It's the same principle. You look for the dosage disequilibrium, you go for the colors, and then you have biomathematicians to figure out the ratios. And this is working now with DNA, so it should be better. And the first publication on this in 2008, but it was very small number of cases, showed 100% accuracy. This was promising, but we have to see big numbers. And this is why it's so good to speak about this topic this month, because as you might know, in January this year, 2 papers came out independently. One is from Hong Kong, in the BMJ, going for trisomy 21, and the other one is from Sequenom, and they used a pretty similar technique. Actually, what you do is, you only need nowadays less than 5 milliliters of plasma. You use next generation sequencing so that you can do this massive parallel sequencing. Usually most places use the Illumina machines, and then you do these different runs. Either you do an 8-plex analysis or a 2-plex analysis, and you see here with the 8-plex analysis 99% positive predictive value. And in the Sequenom study, it was about the same, negative predictive value 100%, specificity 99.8, sensitivity 100%. So what we can say now, this is really the same results in big numbers of cases, that this method is there. It's currently in the approval process with FDA. I think we will try to do the same in Europe. And then finally, chromosomes can be diagnosed using this methodology. So I summarize, a non-invasive prenatal diagnosis has been investigated for more than 20 years, a lot of frustrations in between. People were asking, why is it finally coming? But then I always remind ourselves of the story of in vitro fertilization. Edwards was told in '78 to give up before Louise Brown was born. It's possible now for rhesus and for the other blood group incompatibilities. It's possible for sexing. It's possible for autosomal dominant diseases if they are inherited through the paternal line. It's possible for some autosomal recessive diseases. And I personally think that finally in 2011 we have reached a stage where it's possible for chromosomes as well. Thank you very much. So this was 20 years of research in 15 minutes.